Welcome to our video on 14.3 congruence. And to get this video started, I just want to start right away with some motivation. Are these two shapes you see the same? So I'm talking about this shape and this shape. So it shouldn't take your brain very long to feel like they are the same, right? What's the difference? Well, one of them is more to the right, and then it's also kind of rotated. Okay. So how can we see this using the tools that we've built in this chapter? So this chapter has all been about transformation so far, right? And the first section we talked about translations, rotations, and reflections. And then in section 2, we said we can use these things to find symmetries. Or we can classify types of symmetries rather using these transformations. I now want to use these things to show you that these two shapes have to be the same. And here's how we're going to do it. Let me start by making a duplicate of this shape. And I'll change the color. So it starts here, right? That's where the shape starts. So here's how I'm going to do it. I'm going to shift it over to the right. And now it lands there. So what did we do to do that? Well, I took my points and I shifted over by so many units. In this case, this is, whoa, that's not what I wanted to do. Bring that back, please. There we go. 11 units. I'm just counting the number of grid lines there. Okay, now what do we do? So here's what I claim. I claim I can treat this as the center of rotation for a 90-degree rotation. So when I do this, so of course, a vertical line and a horizontal line, those meet at a 90-degree angle. So when I rotate, this point right here will end up over here. And then I just want you to use your brain to kind of imagine everything else. For example, this point right here, if I rotate that by 90 degrees about this point, it should come around and stop where it shows up at 90 degrees. And remember, it has to stay the same distance from that yellow point. So that point's there. And using a similar reasoning, this point right here ends up there. And so what I'm showing you is that the answer to this question is yes, because we can translate the left picture right 11 units and rotate by 90 degrees. About, let's just call it point Q, and we'll go back and give it that name, Q. Okay, so are these two shapes here and here the same? Yeah, definitely. We can tell that just by looking at it. But how would I actually rigorously argue it to you? How could I prove that it's true? Well, you would probably just take, if these were like physical copies in the real world, you would pick one up, walk it over to the other, and spin it around until it lies right on top of the other. And that's basically what we just did, just using the tools we've developed in our section. So when two shapes can be made to look the same, this is what we mean by congruence. We say two shapes are congruent if applying at least one of either rotation, translation, or reflection to one shape ends up getting us to the other shape. Applying, there we go. So the thing I want you to think is, so this is like the big picture of what to think here. okay? By using a rotation, translation, or reflection, we're hoping that we get one shape to land on the other, just like we did here. And again, I want you to think about doing these things. These are very natural things to do. Like in the real world, we can pick up objects, we can move them, we can rotate them, we can reflect them. That just means like flipping it over, right? So we're just saying two things are the same if I can move them and flip them around and get them to land on top of each other. And the intuition, again, is same shape, same size. Okay. Now, if every single time I wanted to ask you this question, are these shapes the same? Are these shapes the same? And you had to do all this process of translating it, rotating it, maybe reflecting it, that could get a little tedious. And so it would be really nice if we had nifty tools or a nifty mechanism to just say things are congruent, things are the same, without us having to appeal to transformations at all. And that's what this section is really about. So let's just think about shapes. If I draw two shapes, what would be a minimum requirement we would need for them to be considered the same shape, for them to be congruent? What do we really need for two pictures to look the same? Well, here's an idea. Certainly, the side lengths have to be the same, right? If I have two shapes that are congruent, like let's draw maybe two rectangles. This rectangle here and this rectangle here, those are definitely congruent, right? Those are definitely the same because, I can translate and rotate one to get on the other, but also notice the side lengths definitely have to be the same, right? If these side lengths are not the same, there's no way they could be congruent. Same goes for up here, right? We can't really label the distances, but this length better be the same as that length, then that length better be the same as that length, and so on and so forth. So this idea is like a pretty good idea. At the very least, we need side lengths to be the same if they're going to be congruent. So now the question is that enough? And for quadrilaterals, the answer is already no. For example, look at these two rhombuses I have here. So I used this little ruler I have, and I made sure these side lengths were all the same. Yeah, at this point, I'm not really using the grid lines anymore. So let's get rid of the grid lines, so it's less busy. So I basically sat and I measured using this ruler how many units it's going by. And so the point is that on these two on these two rhombuses, which remember, you're a rhombus if all sides have the same length, I've drawn two different rhombuses, but these are definitely not congruent, right? If I take one and I put it on top of the other, there's no way I can make this one the same shape by adding rotation or reflection to this, right? So it's just not the case that rhombuses give you this, or rather, rhombuses do not satisfy this rule because these all have 4 units as their side lengths, so all the side lengths are 4, yet these are not congruent. This also works for parallelograms. Here are two parallelograms, where remember, parallelograms means you have two pairs of parallel sides. So this parallelogram is also just a rectangle. And in both of these cases, they have the same side lengths, right? They have two sides of length 2. And they also have two sides of length 5. So they have the same side lengths, but they're not congruent. There's no way I could take this, I could bring it over here, rotate it, reflect it, whatever. There's nothing I can really do to make this work. So that just doesn't work out. So this idea for quadrilaterals, even though we need it to be true for two shapes to be the same, just having just because your side lengths are the same does not mean the shapes are congruent, unless you are a triangle. So in fact, there is a statement which is called the side-side-side congruence for triangles. And it says any triangle with side lengths A, B, C is congruent to all other triangles with side lengths A, B, and C. What that means is if you draw two triangles with the same side lengths, there has to be a way to rotate it, reflect it, move it around so that it lands on the other one. This might sound obvious, but remember, it already failed for quadrilaterals. This rectangle and parallelogram had the same side lengths, but they weren't congruent. I can't put one on top of the other. Yet for triangles, I'm claiming no matter how you draw two triangles with the same side lengths, they always have to land on top of each other, which is a really powerful statement. So let's explain why these triangles here are congruent without using transformations. So if we were allowed to use transformations, it's kind of clear, right? I can do a reflection across this line, and then one will land on the other, and that's what it means to be congruent, is if they're the same shape. And so reflections would give it to us, but let's not use that. Are we able to prove that these shapes are the same lengths? So I know I got rid of my grid lines, but I think I actually did want the grid lines here. Cool, okay. So in this case, notice these two distances are the same, right? Here to here. They share those two distances. So those are definitely the same distance of 2 units. So let's just say they're inches. And here, yeah, so I should have actually just labeled these. So these aren't going to be exactly right. This picture isn't to scale, but let's just assume I actually gave you these dimensions. I think my intention was for something else to happen, but I just realized that it won't work out the way I drew it. All right, so are these two triangles congruent? So the answer is yes. They are congruent by SSS since they both have side lengths 3, 2, and 4. Right, so by side, since both triangles have a side of length 2, 3, and 4, they must be the same triangle. Okay? Yeah, so again, I think I had a different plan for this originally, which is why I didn't put labels there, but I just realized that I don't actually want that. So anyways, that's how we use side, side. If we know two triangles have the same dimensions, they must be congruent. But why is side, side actually true? Why is it that if two triangles have the same side lengths, they have to give you the same shape? So some of you may not be excited about this, but we can actually use something we learned in chapter 10 to do this. Let's construct a triangle with these side lengths, 5, 4, and 3. So we know how to do that, right? Let's pick a side length. So I'll pick my 5 first. So I'm going to use the grid lines as my units. 1, 2, 3, 4, 5. So there's my length 5 side. And now, how do I figure out how to construct a circle so that the other two side lengths are 4 units and 3 units? This should start feeling like one of our learning objectives. In fact, it's learning objective 2. Using a compass, which I don't have, but I can use circles, because circles are doing what compasses do. Here is a circle of radius 3 units. You can see the units, right? 1, 2, 3. So every point on this circle has distance 3 units from the center. And I can do the same thing and build a circle with radius 4 units. There we go. And what was the magical trick we can do from here? Well, now we know that this point in the middle where they hit makes it possible to now construct a triangle. And what was the big point? The big point was that this is a triangle of the right lengths because every point on one circle has distance 3 units from one endpoint. Every point on the other circle, the one I'm doing right now, has distance 4 units from the other point. And so the resulting triangle must have the correct dimensions. Okay, but this isn't the only triangle this constructs. I also get a second triangle from down here. So, okay, great, cool. What were we trying to do again? Right, we're trying to show that if two triangles have the same sides, they have to be congruent. They have to be the same. So right now, what was the first choice I made? I started by drawing a length 5, drawing a side of length 5. From there, to construct a triangle, I used circles, and I ended up with only 2 options for where I could draw my last point, right? This 5 unit side had 2 points, so I ended up with only 2 more options. And these are the only 2 other triangles. And so now the question is this top yellow triangle congruent to this green triangle? And the answer is definitely yes, because you can just reflect across this line and one of these triangles will land on the other, right? This guy should travel the same distance to get to this horizontal green line as this line does to get to the other point. So this is why side, side, side works. It's because once you specify one side of a triangle, there are only 2 possible ways to construct a triangle using our constructions from chapter 10. So it's kind of ridiculous that that tool all the way from way back then actually proves why SSS works. Take a moment and pause and maybe rewind the video if you didn't quite follow that, or ask me for help on it, because I think it's a really cool thing that you guys have the ability to understand using the tools in this class. But the basic punchline is, given 3 side lengths, you draw one side, and then using our tools to draw the other 2 sides, you can only end up with 2 triangles, but they have to be congruent because of reflections. So side, side, side isn't the only tool that we have in our arsenal. There's also something called angle, side angle. And what you need for this to happen is to have 2 angles with a side in between, and you need that configuration to match in both cases. And by both cases, I mean in both triangles. So let's look at an example, and I think the example will make what ASA is very clear. So can we use side, side, side to determine that these triangles are congruent? So what do I need to do side, side, side? I need 3 side lengths. And in this picture, I've only drawn for us 1 side length. So the answer is no, because we need to know all three side lengths from both triangles. To use side, side, side. Okay. What about ASA? Whoops. I accidentally deleted a part of this question. Use. There we go. There was meant to be a follow-up. Can we use angle, side, angle? So the answer is yes. We can use angle, side, angle because we have an angle, a side, and another angle. And in the same way, we have the same 30-degree angle, the same 4 inches side, and the same 90-degree angle. So it's really important that the angle, the sides are in between the angles. Come on. There we go. So for example, this side right here is not in between those two, the 30 degrees and the 90 degrees, and so we couldn't use it in that case. So when we say angle, side, angle, the side we're dealing with has to be in between the two angles. All right. Can we use angle, side, angle here? So the answer is no, because even though we do have a side in between two angles in both cases, right? The side lengths are different. So the point is, for ASA to work, you've got to have two angles on the outside of a side, and you also have to be able to have all those dimensions match up. Okay, so that is angle, side, angle. There's also one for side, angle, side. So if you have two sides and the angle is the same in between in both triangles, we can also use one of these tools. So here's a problem. And it works out that every isosceles triangle breaks up into two congruent right triangles. And so just looking at this picture right here, you can probably see it. You can see the two right triangles. But let's use SAS, side, angle, side, to show this. So we drop this dashed line down, which means we have a right angle right here, right? So we have this point here now. Let's call this D. So to use side, angle, side, we've got to have a side, an angle, and a side. So here's my claim. Let's use this side, angle here, and this side, and also that side. So both triangles, oh, and just to be clear, my triangles here are BDC and BAD. So both triangles have side length BD, right? Both triangles, this triangle here green triangle and the purple triangle, they both have side length BD. It's the same side, so it has to be the same length. A 90-degree angle. I'll just say and a 90-degree angle. So in order for this to work out, we need to be able to argue that AD equals DC, because then I'll have a side, an angle, and a side. And in fact, we do have that AD equals DC because the line BD splits the whole line AC in half. So indeed, we have a side, an angle, and a side, because AD equals DC. AD equals DC. We then have an angle of 90 degrees in between, and then the last side, BD, is shared by both triangles. All right, can we use side, side, side to show this? So again, if I label this as D, so we know both triangles have side length BD. And we also already know that AD equals DC by what we just talked about in the first part. So we know both triangles have this side. They both have this side. Oops, that's not what I wanted to do. So the last remaining question is, does AB equal BC? And the answer is yes, because if we go back to the beginning, they told us that this is an isosceles triangle. Those are the two sides that were meant to be the same. So we can just wrap this up and say AB equals AC because the triangle is isosceles. So by SSS, triangle ABD equals ADC. And actually, in this prior problem above, I should have concluded by saying, so by SAS, ADB is congruent to ADC. And I just realized I wrote equals to down here. I should write is congruent to ADC. Okay. So that's kind of cool. It's a cool fact that an isosceles triangle can break up into two congruent right triangles. So these three things we've just talked about, side, 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 and angle, side, angle, are all known as congruence criteria, specifically for triangles. They say if two triangles have three sides in common, or they have two sides with an angle in between in common, or they have two angles with a side in between in common, then the two triangles must be congruent. Sometimes some problems are a little bit more challenging. Let's talk about why these triangles are congruent. And then we're going to use this to conclude that angles A and B are equal. Okay. I want you to pause and try to do this problem. In particular, to do this problem, try to think about tools we know from Chapter 10, specifically the beginning of the semester, the first day of class. Pause the video, spend no more than 3 minutes. Okay, so we only have 3 congruence criterion. We have side, angle, side, angle, and side, side, side. We immediately can't use side, side, side because it's just not very clear. These 2 side lengths are the same and these 2 side lengths are the same. On the homework, it's going to be very difficult. You can't use anything you don't know. Even if things look like they're the same, you can't use it. You have to be able to show it. So I only know these 2 sides are the same. And I also know these 2 angles are the same. So let's think. My 3 congruence criterion are side, 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 angle, sine, angle. I can't use side, side, side because I only know one side. And again, I can't use side, angle, side because I, again, only know one side. So there must be a way to use angle, side, angle. And if I'm going to use angle, side, angle, if this is the angle and this is the side, then there is no choice for the other angle. This must be the other angle because the side and angle, side, angle has to be in between your 2 angles. So let's call this angle C and angle D. Are these equal? So ignore the big picture and you should be able to see 2 lines. Gosh, I can't draw lines. There we go. This should remind you that opposite angles are always equal. So C equals D, since opposite angles are equal, so by angle, side, angle, the 2 triangles are congruent. Kind of cool. And if the 2 triangles are congruent, that means that everything matches. They're the same shape. So this 20 degrees matches that 20 degrees. Angle C equals angle D. And therefore, angle A has to equal B. Hence, A equals B, since these are the only remaining unpaired angles. Okay, so I want you to think about this problem when you're doing problem 10. Problem 10 says to do something and then to conclude that certain angles are equal. So this part is kind of like what I wanted you to take away from this. And also with regards to using things like opposite angles being equal and other stuff from 10.1, like maybe parallel postulate, hint, hint, hint. Think about that when you're doing problem 9. So problem 9 and 10 are a little bit more challenging, but you totally have the tools to do them. You just have to be creative and use things like the fact that we know opposite angles are equal. And now I want to make 2 warnings. I put a big glittery colorful star next to it. First of all, please make sure you're copying and modifying your diagrams in the homework to support your answers. So just like here, how I drew C and D, or up here when I maybe drew like extra stuff on top to make it clear what I'm doing. Make sure you're like drawing additional stuff on top of the pictures. Also, I made a comment on this earlier. Don't try to use anything about how the pictures look. Even if it looked like, for example, this side here and this side here, they kind of look the same length, but you can't just arbitrarily decide they're the same length. You're also not expected to be taking out a ruler and measuring the lengths of those sides. You are actually being expected to use just the picture and tools like opposite angles being equal, parallel postulate, etc. Those are the only things you have in order to show that these things are true using angle, side, 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 or side, angle, side. Okay, let's do one final problem. Triangle ABC has side BC length 5. So let's draw a random triangle without really caring too much about it. ABC. Whoa, that's not what I mean. That's what I mean. So BC is 5 inches. Angle B is 20. Angle C is 70. So are all triangles with this description congruent to one another? So let's see. If I drew another triangle and I called it CDE, and it also had something like 20 degrees, 5 degrees, or 5 like 5, 70, do those have to be the same? Pause the video, spend 30 seconds, try to see if you can figure it out. The answer is yes, because of angle, side, angle. By angle, side, angle, all triangles with this specification are congruent. Okay? Again, we're just using the fact that if you have an angle, a side, and an angle that determines the shape of the triangle, they're all congruent by ASA. All right, what if instead we didn't have angle C, but instead we had side AC length 3? So let me start by drawing a sketch. A, B, C. We still had this 20, we still had this 5, but instead of angle C, we know AC is length 3. Are there multiple triangles with that dimension? Well, let's try using the tools that we have. Can we use side, side, side? Nope, we don't know the third side and we can't find it. We could only find it if this was a right triangle, but maybe it's not. Okay, can we use side, angle, side? Well, I do have two sides, but the angle I have would have to be this angle here in order to use side, angle, side, but I only have this angle up here. So I can't use side, angle, side. Can I use angle, side, angle? No, I only have one angle. So none of my congruence tests work, or none of them apply. Does that mean they're not the same? Does that mean there are possibly two triangles that are not congruent with this specification? The answer is actually yes. There are two triangles. They are not congruent. So here's 1, 2, 3, 4, 5. I overshot it a little. There we go. So I want, let's treat this as B, this as C, right? And we know that angle B, at angle B, we have a 20-degree angle. So I can actually use my ruler tool here. So I'm just going to draw a line, and it goes really far because I don't know really where it needs to end. The question is, are there multiple places where I could draw 3 units and get this to work out? So first, Oh, you know what? Let's not use the grid lines. I forgot about this. The ruler doesn't work well with the grid lines, unfortunately. So let's forget about the grid lines. And let's just use the ruler to draw 5 units. So that's 1, 2, 3, 4, 5. So this will be our A, our B, and our C. And this is 5 units. And let's form a 20-degree angle. And again, let's just draw a super long line. Okay. So how do I reach 3 units? So this is 1, 2, 3. So if I finagle around, I claim that I have a 3-inch guy right there. So if you look, here is, so it starts at this marker and it goes 1, 2, come on, 2, there we go, and 3. So this has length 3 units. And so that could be a possible A value. And there's our 3 units. But also, oh wow, I drew this almost perfectly by accident. That's amazing. It's as if I've thought about this before. So now notice here on the ruler with the same reasoning, 1, 2, 3. That's also 3 units long. So this is like another choice for A, where this would be 3 units. So this might be a little tricky to see what I really mean here. So let me maybe make 2 copies of this now that I've done all of this work. So what I am saying is, this description for a triangle is not enough because I've got 2 triangles with this specification. I was able to build this triangle right here so that I had 5 units, 3 units. Oh yeah, and don't forget, we also actually had 20 degrees right here. But also, we could also construct that triangle. And these are definitely not congruent shapes, right? These are not the same shapes. There's no way I could just rotate, translate, whatever. There's nothing I could do to make these lie on top of each other. And so I have to now tell you, in general, in this scenario, when you have an angle, a side, so notice B is an angle, and I have an angle, a side, and then a side, right? So in this scenario, we have A, S, S. And we don't want to tell our kids about S now, do we? So yes, I'm being a little cute here about this, but yeah, it spells ass, and it's ass because it just doesn't work. This is an ass tool. Don't let anyone tell you that if you have an angle followed by a side and a side, that it's gonna work. It's not. It's ass. Okay, I've had enough fun saying that word a bunch of times. So I thought this was cool because I remember learning about ASS at some point and then laughing and being like, haha, it says ass, haha. But the point of that is it's kind of a nice thing to remember that's a tool that cannot be used to show that 2 triangles are congruent, because always in those scenarios, you could probably build 2 different triangles that are not congruent. Okay, and that's basically it for this section. Today was all about congruence and showing 1 or 2 shapes the same, specifically 1 or 2 triangles. the same. And we can use angle, side, angle. This is like I think this would be like a nice little summary. So what do we need to know? We either need to know we have the angle. So if I have two triangles and I don't know they're the same or not, instead of doing rotations and reflections and translations, I can either check that all three sides are the same length, and then I can say by side, 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 these are the same triangles. If I have a side, an angle, and a side, side, angle, side, then these triangles are also the same. That's side, angle, side. I can also have an angle, a side, and an angle, a side, and an angle. And in this case, they're also the same, side, angle, side. But where those things come up is really important. As I just showed you, if you have an angle, a side, and a side, that may not be enough to conclude that an angle, a side, and a side are all the same. They may be different, okay? And that's it. That's what today's about. So on the homework, you're basically going to be practicing applying and using when congruence tools apply. Problem 2 is going to be a lot like this one, as well as problem 1 similar. For problem 2 and problem 1, you are going to need a ruler and a compass in order to do those problems. You're going to have to you're going to have to build constructions kind of like what we used to do in at the beginning of the semester. So in this case, I drew a rough picture, but I am expecting that you use that you actually use a compass and ruler to draw them. So like in this example, in this problem, for example, I just gave a rough sketch, but on your homework, I do want you to use your protractor and compass to construct these things perfectly. Okay, and that's it. This has been Congruences.